Okay, goal here is just to analyze this function, just like we've been doing. So we want to know where relative extrema are. We want to maybe be able to tell where the intervals are, where the function's increasing and decreasing. But I want to add some new stuff. Also, we'll do the regular stuff plus what happened there?
How did you do that?
I don't know. Somehow it turned that into writing. I don't even know what I did, but I'll take it. That was kind of cool.
How did you do that? Whoa. It switched his writing into like what? That's so tricky, man.
I just wish I knew what I did. I'd like to be able to do that again. That was kind of cool.
You like wrote out regular stuff and then clicked something and it turned into print.
What did I click?
I think it just clicks on the. I think you have to use
Right there? Is that it?
Really smart.
What's that thing? Grid designer? No. I know there is a thing where you can do that. I'll start using that more. Regular stuff plus inflection points, stuff we talked about last week, just started talking about, and concavity. Let's see if I can convert to text right there. Hey, how about that? That is, whoops, I won't do that. That is kind of funny. We got a new, this is the new software for this stuff. It's got more bells and whistles. Okay, so inflection points and concavity. Now, real quick, just remind me, what in the world is that stuff? What's an inflection point? What's concavity? What's it have to do with?
Like the bowl.
Okay, good. The bowl analogy, right? We said concave up was bowl-shaped up, essentially. Concave down is bowl-shaped down, right? And where does that come from? You know, we talk about increasing and decreasing. That's first derivative. Okay, good. So it's the second derivative this time, right? The first derivative we associate with slope stuff, so increasing and decreasing, right? And then our first derivative test allows us to find peaks and valleys, right, relative extrema, by just looking at intervals. Well, if we find critical numbers, we know that if we're going through a critical number, if we're increasing to a critical number and then decreasing coming out of a critical number, we know that's peak, right, because it's going uphill and then downhill. Okay, so that's first derivative stuff. Now, second derivative stuff involves concavity and inflection points, but we're going to learn a great trick today. The second derivative is also provides us with a really efficient way of determining what are critical numbers. Are they peaks or are they valleys or are they neither? Okay. So we'll go through a couple examples with this, and I think the process of going through the examples will make this real clear how this works. So what do we got to do to this function then? Okay, we got to differentiate. In fact, we probably got to differentiate twice, right? So what is f prime? Okay, so there's our first derivative. Now let's just pause there and see if we can find our critical numbers. How about? So first derivative critical numbers, where do we find them? Okay, set it equal to 0. So where the derivative equals 0, what's the other place? Well, I shouldn't say the place. Under what conditions of the first derivative could we also find undefined? Okay. So, and I always like to start with that one because that's the one that's easy to forget. Is that function undefined anywhere? No. Polynomial. Polynomials are well behaved. No problem with polynomials. So that is defined everywhere, but may have zeros, right? So we want to set up an equation where we set that equal to 0 and solve. Okay, so talk me through the algebra there. What are we going to do? Okay, I could pull an x squared out.
Take 4x squared.
4x squared, okay, good, could do that. Can I divide anything away here?
Yeah.
Remember, I can't divide variables, but I can divide both sides by constants, right? You might as well trim this down a little bit. Let's get rid of the 4's. I could divide a 4 all the way through, and while I'm at it, if I factored out an x squared then, what am I left with? Does that make sense? So we'll get rid of the 4's and then factor out an x squared. Okay? So what are my critical numbers then? 0 and 3. Good. Okay, now what? Got to have a second derivative. So we'll go back up to here and differentiate again. What are we going to get? Say it again? 24x. Okay, good. And now we're going to look for the, what's really good about this, what makes this an easy process to assimilate for you guys, because you've already been doing stuff like this, is that it's the same, it's the same story, different chapter. We're going to do the same stuff we did for the first derivative for the second derivative. The critical numbers of the second derivative exist at the same kinds of places that the first derivative critical numbers do. So we want to know where is the second derivative undefined or equal to 0. Only difference being that critical numbers of the second derivative now are going to be places where what can happen? What are we looking for with our critical numbers of the second derivative? First derivative goes with extrema. Second derivative goes with, so if you want to make an analogy, like in those analogy tests, the first derivative is to extrema, as the second derivative is to, and specifically points of inflection. You're right. The second derivative, the sign of the second derivative tells us concavity, just like the sign of the first derivative tells us increasing or decreasing, right? Places of transition of those things. If we're transitioning from increasing to decreasing or vice versa, we call that an extremum, right? Peak or a valley. If we're transitioning from upward concavity, positive concavity, to negative downward concavity, or vice versa, we call that a point of inflection or inflection point. Does that make sense? How there's just this parallel setup here? So when we're looking for these inflection points, we're going to set up critical numbers just like we did before. So second derivative critical numbers now. Are there any places where that second derivative is undefined? No. But maybe equal to 0. So let's set it equal to 0 and solve. We can pare it down a little bit. We can divide both sides by 12. Okay. Factor out an x, and I'm left with what? X minus 2 then? So our second derivative critical numbers are what? Okay, I guess I should do this. Zero and 2. Now notice that the first derivative critical numbers and the second derivative critical numbers both have 0 listed as critical numbers. Now, critical numbers, obviously, it can't be both. And well, maybe it's not obviously. It will be in a moment. A point can't be simultaneously an extremum and an inflection point. It just simply can't work. So it's got to be one or the other. So one of these two is going to lose out here, right? We just don't know which one yet. Okay, we'll find out. But this is either going to be an extremum or a point of inflection. Remember, though, that the critical numbers, they can fail, right? We know, for example, that all extrema occur at first derivative critical numbers, but not all first derivative critical numbers pan out. Some of them are false alarms. Some of them turn out not to be extrema. Same with the second derivative. All points of inflection necessarily occur at second derivative critical numbers. But once again, not all of those second derivative critical numbers are going to work out. Some of them are going to fail. And in this case, we know one of those two is bound to fail. Because one of those will win and one will lose. So let's find out.
Can just wrote it.
Yeah.
Before you flip the page, try and turn that into text.
Oh, okay, well, I'll try. Let's see what happens. I don't think it'll
Try it.
do it because it's not.
Try it.
Now, was I wonder if I was on here. Let me see something. Oh, yeah, see, now I see how it works. When I've got my pen turned on and I click on that little button, then it gives me to convert to text. But it's grayed out because it's got all that other weird stuff it doesn't recognize. All the math stuff. Let's go try it. Yes. Okay. So let's set up our table then. See what's going on. Okay, so we've got our x's. F prime, and now we're adding another wrinkle to that, right? We'll add the F double prime. Okay. So does it specify a domain here? No. So what do we assume? Biggest possible domain. In this case, all reals. So we'll indicate that. So on the entire real line, we've got some critical numbers now. First derivative critical numbers were 0 and 3. So x equals 0 was a place where we had a 0 first derivative, and x equaled 3 was a place that we had a 0 first derivative, right? What about second derivative? Well, 0 and 2. So 0 was a first derivative, was a 0 of the second derivative, as was 2. Okay. Now, how do you suppose we are going to find these inflection points when we know where the critical numbers are? How do we find extrema? If we roll back the movie here a couple of days here, how have you guys been finding extrema with the first derivative of critical numbers? Test points, right? And we just know that wherever we get transitions from positive to negative slope or vice versa, those are extrema, right? Same deal here, right? We know where the potential transition points are of the second derivative. We have to just see if it actually is changing sign there, because changes of sign of the derivative correspond to inflection points in the second derivative case, relative extrema in the first derivative case. So let's pick some test points. Throw some out. -1, why not? Okay, we'll try one over here. So at -1, now notice that also here, that with polynomials, and we deal with polynomials a lot in math. With polynomials, the more you differentiate them, the easier they get, right? Because you're whittling the powers down. Every time you differentiate, the powers incrementally step down by 1, which makes things easier. So, so if we want to analyze the first derivative, the sign of the first derivative, it's pretty easy to do, because here's the second derivative, right? I'm trying to analyze the sign of the second derivative. Here it is, but even better, here it is, right? We've actually got it factored. That's even better, right? And yeah, we took out a 12, but that's not changing the sign, is it? I could have just as easily left that 12 in there. It wouldn't have changed anything. And now we can just look at I've got these two factors. We'll just look at the signs of the two factors, and the product of those signs tells us the overall sign. When x is -1, let me rewrite that. That's kind of messy. Isn't that kind of messy? So we had, there, we'll do that. Okay. So if we look at the signs of the factors, when x is -1, what's the sign of the first factor? Negative. Second factor? Negative. Negative times negative is positive. Okay. See how that's easier than dealing with it up here? Up here we'd have to figure out, well, when we're just adding up terms, it's a little more work. We got to know, yeah, what are the actual values of those terms, so when we subtract them, we know which one wins. But if you're looking at factors, product of factors, you just need signs. That's it. Okay, so that's positive. What's another good test point for us?
1.
1. Okay, when x equals 1, what's the sign of the first factor? Positive. Sign of the second factor?
Negative.
Positive times negative? Negative. Okay, so is that an inflection point? Yeah, it is. We're changing concavity, aren't we? We're changing from upward concavity, positive concavity, to downward, negative concavity. And so that's an inflection point. What's another test point for us? Okay, 2.5. Sure, we could do that. 2.5, what's that going to give us for a sign here? Positive. Positive. So those are both inflection points. How about that? Okay? So if we scoot down a little bit, we know and that 0 that was a critical number of the first derivative, well, first derivative lied to us there. It's lost, right? It ended up being an inflection point. Okay, but we had another 0 of the first derivative. Okay? And we got to know what that is. Well, I would claim now you don't need to do any extra work because you actually know what it is. What is it? Okay, well, I want to know what, these were inflection points. I want to know, is this an extremum? It is. Okay, what kind? No, it's actually not.
It's not extreme.
It is. Now, let me show you something here. I went with this, but I want to kind of rewind just about a minute and a half. This test point of 2.5 that you guys threw at me, which worked, was unnecessary in a way. We didn't really need to do that. In fact, we could have killed 2 birds with 1 stone here in a mathematical sense, metaphorically, if we had just done this. Watch now. This is good. Let's use 3 as a test point of the second derivative. Why not, right? Because the second derivative only has critical numbers at 0 and 2. Now, if we do that, this is really slick. Watch what that does. It tells us a couple things. Well, it tells us that this is an inflection point, for one thing, which was nice to know. But what does this mean? Now, if I have a 0 first derivative, what does that tell me about the function there? Yeah, it's a critical number. But if it's going to be a relative extremum, is it going to be a sharp one or a smooth one? It's going to be a smooth one. How come? You're right. Slope is 0, so we have a horizontal tangent there, don't we? Good. So we know that the tangent line looks like that, doesn't it? Now we couple that with a positive sign of the second derivative, and what did that tell us? Positive second derivative meant concave up. Yeah. So now couple those two things, and you tell me what's going on there. If I have a horizontal tangent line at a place on the curve where it's concave up, what is that? It's going to literally look like that, isn't it? What is that? Well, I mean, it looks like a parabola. We don't know if it's actually it's probably not actually a parabola, but it's a relative minimum, isn't it? You see that? Right? If we have a 0 first derivative coupled with a positive second derivative, the only thing that could be, horizontal tangent line bowl-shaped up is a valley. That's got to be a minimum, doesn't it? Right? Now, what if we'd had a 0 first derivative coupled with a negative second derivative? What would that have been? Yeah, that's going to be horizontal tangent bowl-shaped down, so that's got to be a peak. That's got to be a relative maximum. That's the second derivative test right there. Second derivative test allows us to not have to take test points in the first derivative. See that? All we had to do was at the actual critical number, if we can determine the sign of the second derivative, we don't have to mess around with all those test points anymore. That tells us everything we need to know, right? And so now we've got what we need. If we wanted to try to sketch this curve, we could actually sort of do that. There's x equals 0. We had an inflection point there. Positive concavity here, so we know. And tell you what, let's anchor this thing just a little bit. Let's figure out now with our original function, when x equals 0, wouldn't you agree that my original function is also 0? Right? So we know we've got the point 0. Oops. Got the point 0, 0. And what other ones did we get? 2 and 3. What if we just put 3 in there? If I put 3 in there, what do we get? 3 to the 4th, what's that? 27 minus. No, that's not. That's 81 minus 81, isn't it? Is that 81?
Yeah.
Yeah, it is, isn't it? 27 times 4. No, it's not. It's big. Negative 27 should be. Is the overall result, because I get 81 minus 108. Yeah, so negative 27, so it's down quite a ways. Okay, so even if we just had those 2 points, this thing will obviously be to scale, but we'd have an inflection point there, and then a minimum way down here somewhere. So this isn't to scale at all. And it was bowl-shaped up on this side. I did have a horizontal tangent though, didn't I? Right? So I know it's going to have a horizontal tangent, but now it's got to change concavity, like so. And then this is, this should be swooping way down there, but just does something like that, doesn't it? See how that works? Here's where it's got to be bowl-shaped down for this part right here, right? And then it's another point of inflection right there. That's where it transitions from bowl-shaped down to bowl-shaped up. See how that works? Okay. Let's try maybe one more of those. About, oh, this is a good one. Okay. Okay, what about that one? Same stuff. Let's try to find everything interesting about that. Points of inflection, relative extrema. Okay. First derivative. Okay. And what's that going to give us?
Negative 15x plus 15 squared.
Okay. Critical numbers? Any place where it's undefined? First derivative? No. Okay. But we could find some zeros. Let's go ahead and factor that. Now I'm not gonna, let's factor it first, and then we can divide stuff away later. That way we'll have it in factored form if we want to do the any kind of a test on this thing, first derivative test. So I can take out what negative 15 or 15 doesn't matter. If I take out a negative 15x squared, I'm left with. Okay, good. If I set that equal to 0, when?
X equals 0 and
X equals 0. And then,
square root. So,
did I mess something up there? Oh, it should be -1. Whoops. Yeah, there we go. This should have been a minus, shouldn't it? Thank you. You're right. That should have been a minus. Good. So when x equals 0, or when x equals positive and negative 1, right? Good, because we know that this first factor, 15x squared, negative 15x squared equals 0 when x is 0. But x squared minus 1 equals 0 when x squared equals 1. So plus or minus 1, right? So I get 3 first derivative critical numbers. Okay? All right. So what about second derivative? And we want to use, which of these two forms do we want to differentiate? Factored or unfactored? Unfactored, right? We don't, here we have to use product rule, that'd be a mess. We want to just go from there, differentiate the polynomial version of the first derivative. Much, much easier. Okay, so what's that going to give us?
60x plus 30x.
Okay, good. We could factor out, what, a negative 30x maybe? Leaving us with
X squared, 2x squared.
minus, right? Minus 1, okay? So, equals 0 at x equals 0, or what? Yeah, boy, we better. Look, this one's a little bit harder, isn't it? If we set this one equal to 0, 2x squared minus 1 equals 0, then x squared equals 1/2, right? So x would have to equal plus or minus the square root of 1/2. 1 over the square root of 2. I mean, probably technically we should make it square root of 2 over 2, rationalize the denominator, but who cares? That's really not important. So we get, here's all our critical numbers. So we get a lot of them this time. A lot of them. Okay, so we can make our table where we can see all these guys. Okay, so on the entire real line, because we have no restrictions in our domain, lots of critical numbers. So we had x equals, the least would be negative 1, I guess, right? And then we get negative 1 over root 2, and then we get 0, 1 over root 2, and then 1. Okay? And let's see, we had zeros of the first derivative and zeros of the second derivative. Okay, so now we got to get strategic here. What are we going to do? You might remember, now, where do you think, what would you do? Tell me what you're thinking here.
0.
0. I see lots of zeros. That's pretty good.
Let's start with 0 because it has both the first derivative and second derivative.
Okay.
0.
Okay, but now, good. But what are you going to do with that x equals 0? How are you going to know what's going on with that? Well, it could be. It might be an extremum or it might be an inflection point because it's a critical number of both the first and the second derivative. Okay. So I guess let me ask you this. Could I do the second derivative test on that first derivative critical number 0? I can't really do it, can I? Because it fails. Because the second derivative doesn't have a sign there, right? It's also 0. So I'm going to have to default to something else there. The second derivative test didn't apply. So I can always fall back on some other alternatives. Could I do the second derivative test at x equals negative 1?
Yes.
Yeah.
Sure I could, right? Could I do the first or second derivative test at x equals positive 1?
Yeah.
Yes. Now you might remember me saying this, at the time it probably wasn't that meaningful because we didn't have very many rows to work on, but the further you work down the table, the better off you are. You get much more information. You get more bang for your buck if you're further down the table. So let's do that. Let's go ahead and do the second derivative test at negative 1 and positive 1 for one thing, because it's going to help us in more than one way. So if we analyze the sign of the second derivative, and we have the second derivative factored right here, right? At x equals negative 1, what are we going to get for the sign of the second derivative? What's the first factor going to give us? Positive. Second? At x equals negative 1. It'll be positive also, isn't it? Agreed?
Yeah.
Okay. So we get an overall sign of positive. So we know what that is. What is it?
It's a.
Without that.
Yeah, it's a valid. And this is kind of dorky, but this is the way you can remember it. The second derivative, a positive second derivative means a happy function. It's positive after all, right?
Oh,
yes.
Okay, so there you go, right? Now, x equals positive 1. Let's try the second derivative test there. When x equals positive 1, what's the sign of the first factor in the second derivative? Negative. Second one? Positive. So the overall sign? Negative. And of course, as you were expecting, a negative, that's a sad second derivative, right? So that's a maximum, okay? Okay, now what? Okay, well, we need to know if these are points of inflection, for one thing, right? So now we do have to do some test points. We're kind of stuck doing some test points. 1 over the square root of 2, what's a convenient number if possible, that's between negative 1 over the square root of 2 and 0? 1/2 would work, wouldn't it? Sure. Right, because the smaller the denominator, the bigger the fraction, right? And so the square root of 2 is actually a smaller number than 2. So therefore, 1 over the square root of 2 is a bigger fraction than 1/2. So that would work, sure. So let's test the sign of the second derivative at 1/2. It's going to give us, what, negative, right? And what about here? 1/2 squared is 1/4, right? 2 times 1/4 is 1/2 minus 1. That's negative, right? Okay, so I get negative, hang on. No, that wasn't that positive? Because we get negative 30 times, so positive times negative gives us negative, right? So what is that then? It's going to be an inflection point, isn't it? And we know that if this is concave down, and that's concave up, we can even see exactly what kind of inflection point. Right? It's going from bowl-shaped up to bowl-shaped down. And if you want to, go ahead and sketch that in there. You know it's going to look like that. Okay? Well, let's pick another. How about if we just do, that's supposed to be a negative 1/2, sorry. There's my positive 1/2. Put my positive 1/2 in there. That's going to give me negative and negative, right? Overall sign is positive. So this one's going to go like, it's an inflection point. It's just going to go like this, isn't it? If you want to draw the picture in there. You don't have to. But. And then I already know that this is an inflection point, right? Because I used this in my second derivative test. And so I have another inflection point that's like that. I got it all. How about that? All there. Now you see how efficient that was to work down here on that second derivative line? Gave me everything I needed to know. I never even had to mess with the first derivative. Okay? You get the hang of it? Okay, being as we're almost out of time, I do have one more example I'd like to, this is great, I think I was going to be able to get this in. I want to squeeze one more little one in.
Can you sketch the whole thing?
Yeah, sure.
Little drawings.
Yeah, let's do that. Let me grab this whole thing, and we'll go to the next page. Before I do that, though, let's anchor this a little bit. What about 0? If I plug in 0, I get 0. That's nice, right? So I get the point 0. Whoops. Get the point 0, 0. How about the negative 1 and positive 1? Those ought to be easy. If I put in negative 1, I'm going to get what? Positive 2? Is that right?
Yeah.
Okay. And if I put in positive 1, I'm going to get negative 2, isn't that?
Yeah.
Isn't that right? Yeah. Did I do that backwards? That's not right, is it? Yeah, I got it backwards. This should be positive and that should be negative, right? You guys check me on this. Because that's going to change the sign. That's going to make that positive 3. Yeah, that's right. That's right. Okay. So now let's just let me take a snapshot of that, and we'll go sketch it. So we got all this stuff. What am I doing? You must just wonder sometimes, what is this guy doing? Oh. You ever just feel like a buffoon? Oh! What'd that do? Oh. Let's try that. There we go. Okay. So now, sketch. Okay, so where's 0? There's 0 in the middle. So there's our y-axis. And we had a point at 0, 0, didn't we? Okay. And we knew some points, -1, -2. So if I go back here to -2, -1, sorry. -1, -2. So we're right there, and then we're right about here, right? +1, +2, something like that. So we got some points to kind of anchor this thing. And then we had relative extrema, so we had a, let's see, we had a peak out here, where? Well, that was a peak. Okay, so this is our peak. I kind of compressed it, I guess. This is our valley. This is a point of inflection, and then we had a point of inflection kind of right in there, too. Right? So this thing, I should have spread this out more. Here, I'll tell you what, let's say that's 1/2, and that's 1. This is going to get too hard to draw. So this is -1, and that's going to be +1. How about? So we're going to go our middle. So we're switching concavity from positive to negative in between. So it's going to do something like that. Right? There's where we're going to transition from concave up to concave down, and then back to concave up, and then to concave down, and then to does that make sense? So we had let's flag the inflection points. There's one, there's one. Did I get one extra one in there? That's yeah, I got one extra one in there. Whoops. Doesn't have to look that complicated. Does that make sense? Anyway, something sort of like that. There's our picture. Okay, see if I can do 2-minute one here.
Good luck. Good luck.
F of x equals x to the 4th.
3x, or 4x cubed.
Okay, real quick. Obviously, the only critical number for any of that stuff is 0, right?
Yes, sir.
Okay, so if I want to make my table,
Get this done before the bell went out.
oh man, this would be amazing, huh? Okay, got 0, 0, 0, 0. Pretty boring, right? So what is this thing? Okay, the second derivative test fails, but here's what we do. We're going to choose a quick test point. We're going to try the second derivative. If I put -1 in to the second derivative, I'm going to get back positive, right?
Yes.
put in positive 1 in the second derivative, I get back positive. So here's how you interpret this. If the inflection, if this is concave up here and concave up here, it's impossible for there to be one isolated point where it's anything but concave up. Because the whole idea of concavity depends on the relationship between a point and its neighbors, agreed? How could you have bowl-shaped up unless you had a whole bunch of points linked together in that pattern? So what this defaults to then is, even though the second derivative test failed, this defaults to concave up because of that point is surrounded, so to speak. And it makes sense. We know what the graph looks like. Here's the graph. Right? This is just kind of a flattened parabola. It just looks like that. Okay? So that's real. We'll obviously get back to this. I wanted to try to get this in there though. So if the second derivative test fails, you have to defer to the concavities of test points. If this had been a transition, if I'd gone from positive to negative, then this would have been an inflection point. But it's not. Okay.
Oh wait, they cut you off.
They cut me off.
They still have.
I thought they were gonna do